Okay, let's continue with our steam power cycle or steam cycle. As we have looked yesterday, right? In order to increase the work output of the steam cycle or the Rankine cycle, we are going to incorporate the state of steam going into the turbine as a superheated vapor. Okay, that is the state. And in this case, we have to incorporate a component called superheater in order to get a superheated vapor entering the turbine. Okay, so this is again our superheater from point 4 up to point 6. That is the heat from the boiler itself, and then from 6 to 1 is the heat obtained from the superheater. But as far as the heat supply is concerned, we always assume or we always take the heat supplied from point 4 up to point 1. Okay, state 4 to state 1. So what is our Q in right here? The Q in right here is still the same formula. The Q in so the Q in will be equal to Q for 1. Okay, Q for 1. If we assume the feed water pump is neglected, then the heat input is equal to from 0.3 to 0.4, as though from 0.3 to 0.4, because when W34 is equal to 0, then we have H3 is equal to H4. Okay, and as I mentioned before, this is always our concern, the state 2. The state 2 should be determined before we get the enthalpy, whether the state 2 is mixture or superheated vapor, or in this case, it's being sketched right here. The state 2 is exactly on top of the saturated vapor line. Then it should be H2 is equal to Hg at the pressure of this condenser, right? But please make sure that you get the correct state of 2. For example, if you got the H2 is superheated vapor, then the whole sketch of this you have to redraw back. Okay, you have to redraw it back in order to reflect the true cycle, which is the true state of 2. If mixture, then we sketch as in the mixture region. If state 2 is superheated, then we sketch as superheated. Once we have proven what is actually state 2. How to prove state 2? Anybody can answer? Answer me how to prove state 2. What property that we are going to use in order to determine actually what is state 2. Anybody? Anybody want to have a try? How we are going to look at state 2?
Entropy, sir.
Here we are using P2 and S2, where the S2 is equal to S1. Okay, so in our case, for superheated vapor, again, let us sketch the Ts diagram. This is our Ts diagram. This is the saturation line. So this is our case. Let's say I'm putting right here the state of 2 in mixture region. So this is 1, 2, 3, 4. Okay. So how to, of course, you know that before we answer the question, we should get all the enthalpies. Okay, all the enthalpies. So in order to get what is H1, we are going to use, usually we are going to use P1 and T1. How to get H2, this is H1. How to get H2, we are going to use P2 and also S2, whereby the S2 is equal to S1. Right? If we have isentropic efficiency, so this become 2S, this become state 2. Okay? So from P2, S2S is equal to S1, we are going to have H2S. But if we are involving the isentropic efficiency for the turbine, which is equal to H1 minus H2 divided by H1 minus H2S, then from this equation, we are going to have our H2. Okay? So if there is no isentropic efficiency, then this becomes 2. If there is isentropic efficiency, this is becoming 2S, this is becoming 2 actual. So to get 2S, we use P2 S2S, which is equal to S1. Okay? And then we get the state 2S. After that, we are going to use this formula of isentropic efficiency for turbine. We get H2. And then when we get H2, then we look where is H2 at P2. And then we know whether the H2 or the state 2 mixture or superheated vapor. Okay, so if H2 is greater than Hg2, what do we get? The state? If H2 is greater than Hg2, what is the state? Guys?
Superheated vapor.
Superheated vapor. If H2 is greater than HF2 and less than Hg2, then we are getting mixture. Okay? So that is how we get the H2, H2S, and we prove what is the state of 2. And then, of course, we are getting the H3. What is H3? H3 is equal to HF at P3, where the P3 is equal to P2, and the P2 is equal to the condenser pressure. Okay? The condenser pressure. And how to get the H4? The H4 is equal to H3 plus W34. What is W34? The W34 is equal to V P4 minus P3 equal to 0.01 P4 minus P3. This is in kilojoule over kilogram, and these two values should be put in as kPa. Right? So that's how you get your, when W234 is equal to 0, then you have H3 is equal to H4. Right. So this is what we have looked, the usage of superheated vapor entering the turbine. Why do we need superheated vapor entering the turbine? because we want to increase the work output of the cycle. Okay, we want to increase the work output to the cycle. Then next, what we can do, what like Tiva said yesterday, we also can have the increase in work when we increase the pressure. Now we try to observe, to analyze whether it's true or not. So this is the part whereby we have the increase of pressure. You see? What happened when we increase the pressure? Tiva, where is Tiva? Tiva. You see now, you want to increase the pressure. Why we want to increase the pressure? So that the steam will absorb or will get more energy. If we have more energy in, then we are expecting to get more energy out. In this case, the energy out is in terms of the W from the turbine. Right. Let's say that we have the same fuel use, the LPG or diesel or heavy fuel oil, right? They have a certain or the maximum level of temperature during the combustion. So we cannot increase. That is the maximum value. But when you increase the pressure, can you see what happened to the outlet of the turbine when we increase the pressure? What can we have when we increase the pressure with the same temperature? What happened? Our concern is towards the outlet of the turbine. This part. Okay, this part. What happened when we increase the pressure? The steam coming out from the turbine become wetter. You see? It's wetter. Basah, Dia panggil basah. Water during the expansion process is very bad for the turbine. It's very bad for the turbine. So we are not going to suggest for the pressure to be increased in order to get more work. Okay, more work. We try to avoid that because of this problem. Masih ingat tak kalau siapa yang pernah bawa motor kan, bawa motor masa hujan? Kalau kita punya helmet tak ada visor, apa kita rasa? Naik motor laju-laju tak ada visor. Hujan. Rasa macam ada batu batu dibaling ke muka kita. Sakit kan? Jadi kalau air, okay, kita berada dalam hal laju yang normal lah, katakan 60 km per hour or 70 km per hour, kita dah rasa dah kesakitan tu. Just imagine, the turbine could rotate up to 20 or 30,000 RPM. It's rotating though. The turbine blade is rotating to 20 to 30,000 RPM. And when this high revolution of the turbine hitting liquid, what do you think will happen?
It will destroy the blade, sir.
Yeah, the blade will bend or the blade will damage. Yeah, kalau dalam bahasa Malaysia dikatakan dia sompek. Sompek apa dalam bahasa Inggeris? Apa sompek dalam bahasa Inggeris? I couldn't get the terminology. Sompek.
Is it twisted, doctor?
Bukan twisted one. Tapi sompek, what is sompek? Alamak, dulu saya ingat tu sompek tu. Macam pinggan sompek tau. Macam pinggan sompek macam pinggan kan, kadang-kadang pinggan siap kita sompek. Dented kemek. So, ini dia sompek tau. Dia chip off. Dia chip off. Okay, the turbine blade is chip off. Jadi kalau turbine blade chip off, ataupun maknanya sekarang ni dekat turbine blade tu ada lubang tau. Bila ada lubang, ini bermakna when we inject the steam through the nozzle this hole will becoming bigger and bigger and bigger and bigger. Jadi lama-lama kita punya turbine blade akan fail. Kita punya turbine, the whole turbine will fail. It's very dangerous. So we try to avoid this part. Dan berapakah nilai yang kita hendakkan dia punya X value, the quality? Okay, for your information, in this textbook, they are using dryness fraction. The dryness fraction is actually what we have learned in thermodynamics is called as quality. And this quality, of course, we are going to use the same symbol as X. This is the limitation of X. Paling rendah, the X value is 0.9. So kalau kita increasekan pressure dia, maknanya kita akan dapat more wet. Maknanya kita akan dapati kita punya steam yang keluar dari turbine dia basah. Maybe it could be 0.8 or even 0.7. It's not very good. Okay, it's not very good. Right? So, kita nakkan kerja. What are we discussing right now is to increase the work. As far as we are concerned, we want to increase the work. Right? So, the first method kita increase the work adalah dengan menggunakan superheated vapor. Superheated vapor. Now, kalau kita try to increase the pressure, ini yang berlaku lah. Okay, tiba? So it's not good lah to increase the pressure. That is the drawback yang kita dapat. As far as the engineering application is concerned, that is what will be happen if we increase the. Betul, when we increase the pressure, kita akan bagi more energy to the steam because the boiling point akan meningkat. The Tset will increase when your pressure increases. Jadi to avoid this, to avoid a wet type of steam outlet from the turbine, apa kita buat? Kita gunakan apa yang dikatakan sebagai multi-stage expansion. Okay, multi-stage expansion to further the work output, kita akan incorporatekan multi-stage expansion with reheat. Okay? Meaning what? Meaning we are going to have 2 turbine for the expansion process. Okay? 2 turbine for the expansion process. So, jadi apa kita buat? Kita ada turbine. So, let's say this is the first turbine. This is the second turbine. Okay? So, this is from the boiler. And then after exhausting from the first turbine, let's say this is the high pressure turbine, this is the low pressure turbine. We are going to couple everything together. This is our output. Let's say the output of our turbine is to run a dynamometer or electrical generator. This is the power output. Before that, we have the superheater, and before that, we have a boiler. Okay? And then after that, we have a feed water pump, and then we have the condenser. So this is the outlet. So this is our turbine, high pressure, turbine, low pressure. This is our condenser. This is our feed water pump. This is our boiler. This is our superheater. And as far as the boiler and superheater is concerned, this is the part whereby we are going to put in the heat. Okay, going to put in the heat. So let's say this is 0.1, this is 0.2, sorry. Kenapa saya cakap 1, this 2 This is 1, this is 2, this is 3, this is 4, and this is 5. Alright, so this is our arrow, the direction of the process. Okay, so when we sketch the Tts diagram, for this case, okay, so this is our expansion process. This is the condenser. This is the heat superheater. This is the boiler. This is our pump. Right? And we did 2 expansion process. So meaning that we are going to have an intermediate pressure right here. So when we refer to this schematic diagram, that is 1, 2. Okay, this is state 1, this is state 2. And then this is state 3, this is state 4, and this is state 5. If we look this application of our multi-stage expansion, it does not give us any increment of W net. Because whether we are using only 1 turbine or using 2 turbine, the turbine output is still from 1 to 2, 2 to 3. Okay, 1 to 2. From here, we are getting the work 1, 2. And from here, we are going to have the work 2, 3. As though we are still using 1 turbine. Okay, we are still using 1 turbine. But having a multi-stage expansion process, it will give us the ease of maintenance. Right? And then we could reduce the size of our turbine. We don't need a very big turbine, but we can use a smaller turbine, but we are going to arrange that turbine in series. That's why one is called as the low pressure turbine, and the other one is being called as the high pressure turbine. But as far as the work output from the turbine, it is the same as though that we are having only 1 turbine. There's no increment. Okay, there is no increment of work output. It's still 1 to 3. If we use 1 turbine, also still 1 up to 3. The maximum to the minimum pressure. Okay? But if we use multi-stage expansion with reheat, then we are going to have the increment of work. So how we look the cycle with multi-stage expansion with reheat? So this is how it will look like. Tts diagram, the maximum pressure, which is the boiler pressure. And then we have the minimum pressure, which is the condenser pressure. And then we have one more pressure, which is called as the intermediate pressure. This is still the feed water pump work. Let's say this is the inlet of our first turbine, the high pressure turbine. Then what we are going to have? The first expansion. Okay. After that, what we are going to do? We are going to reheat. We are going to reheat this steam outlet from the high pressure turbine. Then only we are going to expand it to the second turbine, which is the low pressure turbine. You see, when we do this, then we are going to get more work output. Right? And then the processes continues in the condenser, in the feed water pump, and in the boiler superheater. So meaning that we have to change our schematic diagram, whereby from here, we are going to flow the outlet of this turbine again into the place whereby we have the reheat process. Then only we are going to expand in the low pressure turbine. So now we have a new numbering because we have add up another process. So this is still 1. This is 2. Going into the reheat process, then it's going out here is S3. This is S4. This is S5. And this is S6. Right? Then we try to transfer all the numbering to this schematic. This is a Tts diagram. This is 1. This is 2. This is 3. This is 4. This is 5. And this is 6. Okay? So as far as the work is concerned, now we have 2 stages of work. We have work 1, 2, work 3, 4. Okay? So we are going to get all the enthalpies from 1, 2, 3, 4, 5, and 6. Right? Usually, point 1 will be given the P1 and T1. Point 3 will be given the P3, which is the intermediate pressure, and the temperature of T3. This usually is being given. Of course, this is our condenser pressure. It's given. The intermediate pressure right here is equal to P2 and P3, which is referring as the intermediate pressure. This is the P boiler, which is the maximum pressure. Okay, maximum pressure, intermediate pressure, condenser pressure. The boiler pressure, P6 equal to P1. The intermediate pressure, P2 equal to P3. The condenser pressure, P4 equal to P5. Okay, so we are going to use this to get H1. We are going to use this Pi or P2 and S2, which is equal to S1, to get the state of 2. Then we get what is H2. Using P3 and T3 to get H3. Using right here the P4 and also the S4, which is equal to S3, we are going to get H4. H5, of course, HF at condenser pressure. And what is H6? H6 is equal to H5 plus W56. Okay? So this is our Tts diagram. Rankine cycle, multi-stage expansion with reheat. That is what being called of this cycle. Rankine cycle, multi-stage expansion with reheat. Okay, that is the name of this cycle. Before that, we have Rankine cycle with superheated vapor. Before that, Rankine cycle with saturated vapor. Before that, apa dia? Before that apa? Siapa ingat? Before the Rankine cycle with superheated vapor, before that apa? Come on. Guys, apa dia? Jangan lupa. Apa dia?
Carnot cycle.
Apa
Carnot
dia?
cycle.
Carnot cycle, Alif. Betul. For that, we learn about Carnot cycle. So, berapa cycle lah kita belajar? Carnot cycle. Rankine with superheated vapor. Rankine, okay. Carnot cycle, Rankine with saturated vapor. Rankine with superheated vapor. Rankine with multistage. And reheat. Okay? The purpose of Rankine with superheated vapor to increase the work output. The purpose of Rankine multistage plus reheat also to increase the work output. Right. What do you think in terms of the thermal efficiency? What do you think in terms of thermal efficiency? What is the formula of thermal efficiency? So we are looking at multi-stage right now and reheat. So what is our W net? W net is equal to W12 plus W34 minus W56. H1 minus H2, H3 minus H4, H6 minus H5, or V multiplied by P6 minus P5. How about our Q in? The Q in right now is Q61 plus Q23. Okay, this is also the Q in. Okay, this is also the Q in for the reheat. So if we look back at the schematic diagram, we can see that this green dotted line represent the heat supply. Boiler, superheater, reheat. So from 6 to 1, and then from 2 to 3. Okay, 6 to 1, you see, 6 heat supply, 6 to 1 boiler, and then reheat 2 to 3. Although we are getting the work output to be increased, can we say that the thermal efficiency also be increased? So it's very subjective. Although we are having the W net is going to increase, but at the same time, we are also increasing the Q in. So it's a very big question mark whether we are going to have better efficiency or not, because we are increasing both of these two parameters. W net increase, at the same time, Q in also increase. So the purpose of Rankine plus superheated vapor, the purpose is to increase the W net. Rankine plus multistage plus reheat, this is also to increase the W net. Okay, also to increase the W net. What happened to the first Rankine cycle? First Rankine. What is the purpose of Rankine with with saturated vapor? What is the purpose? Anyone? Rankine superheated vapor, Rankine multistage with reheat is to increase the W net. How about Rankine saturated vapor? What is that cycle for? Remember? I did the explanation why we need Rankine saturated vapor. Guys? Any response?
Because the most efficient, doctor.
Most efficient? No, not because of most efficient. This is the purpose of to convert the Carnot cycle towards a more practical and applicable cycle, which is Rankine. Okay, we are converting this type of cycle to this type of cycle. Remember the cycle whereby this is saturated vapor. This is Carnot, this is Rankine. Okay, I just put this diagram to show that this is sketched on the Tts diagram. Okay, so what happened in the Carnot? This side is the compressor, but for Rankine, this side is feed water pump. So we want to change the Carnot cycle more towards a practical cycle that we can build and have the work. Because Carnot cycle is only a theoretical cycle. Okay, it's a theoretical cycle. Okay, any question, guys? So that is the next cycle that we have learned, the multistage with reheat, to further increase the W net. Guys, any question? No question.
I'm okay, Doctor.
No question.
Good. So let us look at the steam cycle. Now let us look at one example. This one. Okay. There's no description on this question, yeah? I just put figures, only figures, right? Can you see, guys?
It's a bit small, Doctor, but okay lah.
Boleh
Boleh,
Atau
boleh.
nak, you want me to do it to bigger it?
Bigger.
Okay, alright, okay. Apa sebab begini? This one, where is, mana dia punya toolbar dia? Come on. Oh, this toolbar dia. Okay, unlock. Delete this first. Okay, nampak?
Nampak.
Okay, a bit blur Sorry about that. Just want to explain all the... Right. So this is very typical what we call as the Rankine cycle with multi-stage expansion and reheat. So this is our multi-stage expansion. 1 to 2 is the turbine high pressure. 3 to 4 is turbine low pressure. And then of course from 6 to 1 is the boiler and also the superheater and also the reheat. Okay, sorry, the reheat is from 2 to 3. But again, we are going to flow in from state 2 again to the boiler side or to the superheater side to be reheated. Okay, and then this is the second expansion, turbine low pressure. The condensate, we throw away the heat in order to condense the steam becoming saturated liquid, and then 5 to 6 is the compression or the pumping work from P5 low pressure to P6 high pressure, boiler pressure, from condenser pressure to... And then we are looking here, this is the pressure of the boiler, the high pressure, 4000 kPa. the intermediate pressure at 600, and then the condenser pressure at 40 kilopascal. And then the T1 is 400 above the critical point, above the critical temperature. And then the T3 is at 600 kPa, which is 350 degrees C, a bit lower than the critical point. So we have to sketch appropriately. A bit lower than the critical point. The critical point is 373. Okay? So this is the temperature involved. And then given the isentropic efficiency for the high pressure turbine and also the low temperature turbine is 0.85. This is the equation correspond to the isentropic efficiency of the high pressure turbine, which is H1 minus H2 divided by H1 minus H2S, whereby the low pressure turbine, the isentropic efficiency is H3 minus H4 divided by H3 minus H4S. Okay? Now, look how do I sketch the cycle. 6 to 1, 1 arrow, and then 1 to 2S, 1 arrow. And then, can you see that 2S to 2, there's no dark line, because this does not present any process. Right? This does not present any process. The process of reheat is starting from 2, the actual condition of the steam coming out from the high pressure turbine. So the reheat process is not from 2S, but is from 2 up to 3. Then we have the second expansion, 3 to 4, the actual expansion, taking care of the isentropic efficiency. 3 to 4S is the ideal expansion, assuming it's reversible and adiabatic or constant entropy. And then if you look, what is the actual condition going into the condenser? The actual condition, the actual state going into the condenser is from state 4. Therefore, the darkened line is starting from 4. Okay? Starting from 4. It does not start from 4S because 4S is not the beginning of the condensation process in the condenser. Because 4S is the ideal case. The actual condition, the actual state going into the condenser is from state 4. That's why the line is darkened from 4 up to 5. Okay, this is also, you know, I explained for this, the actual reheat process is from 2, not 2S. So be careful of sketching and darkening the processes line. Make sure that you are going to sketch the actual. Okay? And again, we should take care of these two states. This state and also this state. Okay, this state and also this state. We don't know where is actually point 2S. It might be mixture, or it might be superheated vapor. Or 2S might be mixture and 2 might be superheat. Or 2S and 2 might be both in mixture region. Same goes for 4S and 4. Both could be superheat. 4S might be in the mixture region. 4 superheated. Or 4S and 4 might be both in the mixture region. So we must take care of this. So along the way, when we are going to determine the enthalpy after this, we are also going to take care of 2s, 2, and also 4s, 4. Right? So before answering the question, of course, what do you think that we are going to have? What type of question that you want? Can we predict in this case? Can you give me suggestion? What are we going to solve for? Number one, what do you think we are going to solve? After learning up to this level of the steam cycle, what do you think that you will ask? The first one.
Work output, sir.
Okay. What is the work output called?
Net work out.
Yes, W net. Second thing, what do you think? What do you think? Anybody? Come on. Yeah, come on, guys, wake up.
Thermal efficiency, sir.
Thermal efficiency. Okay, before we get the thermal efficiency, what we have to determine first?
Q in.
Yeah, our Q in. Yeah, our Q in. Then only we go for the thermal efficiency. After that, what do you think? So thermal efficiency, what do you think?
SSC, Doctor?
Yes, SSC. After that, we are going for SSC. SSC. What do you think the last one?
Ratio.
Yeah, the work ratio. So this is all the parameters that will be asked frequently and often asked in the test or in the question. Either one, or maybe we can change it later. Right? So, before that, what are we going to do? Before that, what are we going to do? Before answering 1 to 5, what are we going to do? Guys, what are you going to do?
Find the H value for all, sir.
Yes, we are going to find all the H value. How many H? Come on. How many in total? We have 6 states, meaning that we are going to have 6 enthalpy. And then we have 2 isentropic efficiency. We are going to have additional 2, meaning that we are going to have 8 enthalpies. 1, 2, 3, 4, 5, 6, 7, 8. 8 enthalpies. Now, can we get what is H1? Can you get the H1 for me? What is H1? 4000 kPa, 400. What do you think the state? Of course, it will be superheated vapor because the T4, the T1 is greater than the T crit. So it's superheated. So you don't need to prove. In applied thermodynamics, you don't need to prove what is the state of 1. Just get the enthalpy. So what is H1? H1, sorry. H1. H1 please. You do it together Jangan saya seorang je buat. Saya dah understand lah. Kalau saya seorang je yang buat.
Doctor, just to confirm, so
Yeah.
superheated vapor at 4 megapascal at 400 degrees Celsius temperature.
Yeah, this is the point.
Okay, the value
Okay.
is, the H value is 3214.5.
3214.5 kilojoule over kilogram. Okay.
Can someone approve that? Just recheck.
Okay. Tiwa want somebody to approve it. Oh, kena approve Alright. Okay, Afiq. Okay.
I got the same answer.
Okay, cantik. The same value Kita tak jawab soalan lagi tau. We haven't answered any question. We are just getting the enthalpy. So what next parameter that we need, do you think? What do you think? What the next parameter that we need?
Enthalpy.
What enthalpy?
S1 equal to
There you see, you need the S1 kan? Bukan you need the enthalpy. The next thing that you need is the S1. Why do you need the S1? Because you know that the S1 is equal to S2S. Betul? So, meaning that when you are getting H1 and this type of expansion process, then you need the 2S, the S2S. Because you are going to use the S2S and P 600 kPa to determine what is H2S. So right now, you need the S1, which is equal to S to S. What is the value?
6.7714.
6.7714 kilojoule over kilogram. Guys, please, when you put any value, there must be a unit. Okay, don't left out the unit. Okay? Next, what are we going to do? Now we are going to have the H2S. How to get the H2S? The H2S is based on the S2S. This is our S2S and pressure of 600. Okay? So now check the S2S whether it is superheated or mixture. How to check that? Look at this value of S2S and compare to the value of this SG, the SG at 600 kPa. Okay? Now, can you compare that for me? And let me know whether it's greater or less than SG. Greater. So you are finding out that the S2S is greater than the SG2. Therefore,
Superheated, sir.
yes, superheated vapor. From this information, then we are going to have our H2S. Now, go to this superheated vapor table at 0.6 megapascal. Try to get the value of this 6.7714 at the superheated table at 0.6 megapascal. Do you have the exact value? So what you do right now, using this value, okay, let me erase this. I want to make use of this diagram ya. Jadi saya padam yang ni lah. We have got the H1 kan. So kita based on this S to S value, Then we are looking at what? We are looking at 0.6 megapascal. Look for this S to S. Water, mana water? Yeah, this water. Okay, buat sama-sama sekejap ya. 0.6 megapascal. 0.6 megapascal superheated vapor. 0.6. Yeah, okay, this is 0.6. The value of S2S is 6.7714. 6.77, yeah. Here you are. Okay, from this point to this point. Okay? So there's no exact value. So what do you have to do? You have to do interpolation.
Interpolate.
Okay, now do your interpolation. Get for me what is your H2S. I'm giving you 5 minutes to do your interpolation. Everybody, please try. Okay, please try. Any problem, we discuss. Okay, what you need to do right now is to look at 0.6 megapascal. Okay, you are going to look for what? You are going to look for your enthalpy. What do you have? You have your S. This is what you want, H2S. This is the enthalpy involved, 6.7714. In between two values of tabulated entropy and correspond to the tabulated enthalpy. Okay, so you refer to your table right here. So it's between 6.7593 and 6.9683. You put this value in your table right here. Then by interpolation, okay guys, now this is the most interesting of applied thermodynamics. You don't need to write your equation. You just put this table, put all the value, then you will get your H2S straight away. You don't need to write down this minus this divided by this minus this equal to this minus this divided by this minus this. But unless you want to. Okay, but as far as I'm concerned, when you put this table at 0.6 in order to determine the H2S, this is enough for me. Because after that, you have memorized how to get the H2S and the equation that you are going to rearrange in order to get H2S. Because this is interpolation. This is not thermodynamic. This is interpolation. It's mathematics. Okay. So what is H2S?
2761.7. 2761.7.
1.67. Okay, 67. Kilojoule over kilogram. And then after that, we have got this. This is settled. Okay, the enthalpy of this is settled. And then the enthalpy of H1 also settled. Okay, this one also settled. Now next we are going to get for the H2. How to get the H2? By using this formula. Okay, so using this formula, you are going to have H2. You put in all the equation. The isentropic efficiency for turbine high pressure equal to H1 minus H2 divided by H1 minus H2S. This is given. This is obtained before. This is already calculated through the interpolation, and then left with H2. Okay, what is your H2? Okay, anybody?
Two 2829.59.
2829.59. Okay, can someone verify that?
Same, Doctor.
Oh, good.
Same, Doctor.
Oh,
Same.
bagus. You all bagus lah. Semua dapat jawapan sama ya. Tak tiru eh?
Tak ada.
Jangan tiru, jangan tiru please. Do your own work. Kan susah pun, senang je ni. It's routine. Okay? So that is your H2. So what's next? We have settled the H2. Now we have to get our H. Do we need to prove what is the state of 2? Okay guys, come on. Do we need to prove the state of 2? Can 2
I think no need, sir.
Can 2 be mixture? What do you think? Now you have gotten that the 2S is superheated vapor. Then the 2 should be to the right of 2S because of the principle of entropy generation. The entropy is always increase. It's always increasing. There's no such thing that the entropy will be less than the 2S. It should be always to the right. Whether we are looking at the expansion process in turbine, or we look in the compression process in the compressor or in the pump, the actual entropy should be always greater than the isentropic entropy. Okay, so we don't need to prove what is the state of 2 because it should be to the right. For sure it will be superheated vapor. Now solve for me the point 3, the H3. What do you think the H3 will be? It will be superheated or it will be mixture? Of course, it's to the right because we are going to increase the energy of 2. When we increase the energy of 2 by reheat, then the state 3 will be further up, further into the superheated vapor. Therefore, you don't need to prove the state of 3. Just look at 0.6 megapascal and 350 degree C. What is the value of H3? Now we are going to solve for H3. Okay, can someone read for me? Just read from the table. H3 is equal to
3166.1.
3166.1. 3166.1. Do you think that we need the S3? Do you think that we need S3?
Yes.
Why?
To find S4.
Yeah, because it's equal to S4S.
S4S.
right? So what is the value of S3?
Um, 7.5481, sir.
7.5481.
Yeah.
7.5481 kilojoule over kilogram Kelvin. So this is S4S. So what's next we have to do? What do you think? Now we have got this S4S. What do you think that we need to do right now? What do you think?
H4S.
Yeah, we already got S4S. S3 is equal to S4S. What do you think we got to do after this? After getting the S4S, which is equal to S3, what do you think that we need to do?
H4S.
How do we get H4S? Can we get H4S without knowing what is the state of 4S? What is your comment? Where to look for H4S? Yes, that's right. We are going to have H4S. My question is, can we get H4S without knowing the state of 4S? Because if 4S in mixture region, to get H4S, we are using different approach. If the H4S in superheated vapor, we are going to refer at the superheated vapor table. So which one are we going to do? Are we going to assume H4S as mixture, or we are going to assume the H4S superheated vapor?
Look at
Bandingkan dengan
table
SG, sir.
for
Yes, meaning
SG.
that the next thing that we could work on is to prove what is the state of 4S. Okay, that's why we need the S4S, which is equal to S3. So now, what are we going to do is to look at the pressure of condenser, to look at the condenser pressure, which is at 40 kPa. Look, where does this S4S fall in what state? Okay, we have the value. Now we want to know the state. Meaning that we are going to get what is this value? Okay, this value. The SG4. You know this value already. You need this SG4. Is the S4S less than SG4? Mixture. If the S4S greater than SG4, superheated vapor. So now let me know what is the magnitude of this S4S compared with the SG. You want to find the state right now. Okay, anybody got it? Anyone? Ni lamanya. Why so long?
Mixture, sir.
Mixture. How come you get mixture?
I'm not sure. Yeah, the SG I get is 7.6691.
SG 7.66.
91.
So this is what you have.
Yeah.
At this 40 kPa, you are going to have the S4S is in between S4S, SF4S, and SG4S. Therefore, mixture. When you find it mixture, what do you have to do next? What do you think that you have to do next?
Find X.
Yes, find the X value. X is equal to S4S minus SF4S divided by SFG4S. So this is X4S. Why do we need this X4S? Because when we want to solve for H4S, because it is mixture, then we have to use this formula. Which is the SF4S plus X4S HFG4S in order to get your H4S. Okay. To get the H4S. But before that, we need to take note that our point 4S is wrong. Okay, our point of 4S is wrong. It's wrongly sketched. Initially, we have drawn this Tts diagram, and during the calculation, we find out that it is not superheated vapor. It is actually at mixture. So this is wrong. We need to correct it later. Okay, just use this Tts diagram for our guidance in order to solve all the enthalpies. Okay, now give me your X value, and after that, get your H4S. Okay, anyone got your H4S?
So is it 2589.65?
Berapa?
2589.65?
25?
Yeah.
Berapa?
No?
Again?
2589.
25. Your what? Your X4. X4S.
No,
X4S.
H4S.
Yeah.
317.
317?
HF4S. Oh, X.
No, X.
0.982.
Yeah.
0.98.
0.98.
4 decimal point.
0.9818.
Okay, 9818. Oh, you terus baca ni tadi Oh, patut lah. Saya minta the X value first. Okay, now you already got H4S. What is the value? I thought somebody has said it just now. Betul?
2593
259
3.8
3.8. Another one?
3.
3. Okay, now you already solved for your H4S. Next, you are going to solve for your H4. The actual condition, H4. So by using the isentropic efficiency for the turbine low pressure, which is equal to H3 minus H4 divided by H3 minus H4S. Given isentropic efficiency, H3, we have solved it before this, H3 and H4S, then left with H4. Can you calculate what is H4?
Two six seven 269.67.
2679, 2679.
67.
Okay, can someone verify that? Can someone verify this value?
Yes, Sam, sir.
Okay, thank you very much. So what's next, guys? What's next? What do you think that we are going to do next? Macam mana? Senyap This is already wrong, right? How about this 4? Is it correct, the state? So the next thing that we got to do is to look what is actually the state of 4. Right? Just now we have proven that the state of 4S is mixture. Is 4 also mixture? Or is 4 at superheated vapor? Okay? So now we have to prove it. How to prove it? By looking at this Hg4, this value. Compare with H4. So what we do? Add 40 kPa. Compare this value with the value of Hg, Hf at 40 kPa. Betul kan? 40 kPa kan kita punya? Ya, 40 kPa. Betul.
Higher.
So,
Yeah.
do you compare that? And look where is actually the state of 4?
Higher, sir. Superheated.
Higher, right? So you are getting that the H4 is greater than Hg4. Therefore, superheated vapor. So now, can you imagine that the 4S is mixture and the 4 is superheated vapor. So we need to correct our Tts diagram. But before we do the Tts diagram, I think we get all the enthalpy first. Right? So solve for H4. Next is what? H5. What is H5? Hf at 40 kPa. What is that?
317.62.
Okay, 317.62
62.
from the table, right?
Yeah.
Kilojoule over kilogram. Next, we are going to have our H6. What is our H6? Is equal to H5 plus W56. What is W56? Is equal to 0.001 P6 minus P5. So put the P6 and P5 in kPa. So can you calculate for me? This is 600, right? 4,000. 4,000 minus 40. So can you give me the value of W56? 4,000 minus 40 multiplied by 0.001. It should be
3.96.
3.96 kilojoule over kilogram. Then we get H6, which is 317.62 plus 3.96. So what is our H6?
321.58 kilojoules
58 kilojoule.
per
Correct?
kilogram. Yep.
58 kilojoule over kilogram. So guys, now we have all the enthalpies. Before we calculate number 1 up to number 5, then I would suggest you to sketch the Tts diagram. Okay. This one is but a bit tricky. Kadang-kadang kita buat first time tak semestinya betul. But we might have to adjust all the point. So let me put right here. Okay, I want the point of, this is our point. One is inside. Another one is outside. We have to adjust it. Okay, this one is outside. This one also outside. So kita kena adjust lah, tipu-tipu sikit lah. So this is our pressure, this is our pressure. Sorry. Okay, so let me highlight it. Sorry lah guys, tangan tak stable lah. Okay, but you got the idea kan? And you all tangan masih muda lagi Jangan ikut macam saya Gigil. Kalau gunakan tablet. Kalau gunakan whiteboard tu sedap sikit. Okay. This one. Okay. So this is 1, 2s, 2, 3, 4s, 4, 5, and 6. Don't forget your arrow. Because we need the arrow that represent the direction of the process. Again, you see, for the reheat process, starting from 2 to 3. For the condensation process, beginning at 4 to 5. Okay? So this is our corrected Tts diagram. Now you can get what is being asked for number 1. What is our W net? The W net is equal to W12 plus W34 minus W56. What is W12? W12 is equal to H1 minus H2. You already got your value. Right? W34 is equal to H3 minus H4. And W56, we have solved before this when we tried to get the H6. Then you get your W net. Number 2, Q in. Q in is equal to Q in the boiler and superheater, Q61. Boiler, superheater. Boiler, okay, boiler 6 to this point, superheater from this point to this point. And then, plus the heat input for the reheat process, 2 to 3. From 2 to 3, the reheat process. So what is Q61 is equal to H1 minus H6. And then Q reheat, Q23 is equal to H3 minus H2. Then solve for your Q in. You've got your enthalpies already. Next, what is our thermal efficiency? Number 3. Thermal efficiency for this Rankine cycle is equal to W net divided by Q in. And then don't forget, this is always put in terms of percentage. Then you have to get it, multiply it by 100. Number 4 is the SSC equal to 3600 divided by W net. And this W net, put in the unit of kilojoule over kilogram, then automatically you are getting in terms of kilogram over kilowatt hour. And lastly is to get the work ratio. What is the work ratio? The work net divided by the work gross, which is equal to W net, and the work gross is W12 plus W34. So this is, you are getting in terms of fraction, 0 point something. Okay? So that is how you are looking at this. Any question? Any question, guys?
Just mind blown, doctor.
Just what?
Mind blown.
Pardon? I don't get it.
Mind blown, mind blown.
Again, Tiba, I don't get it. I don't understand.
Mind blown, doctor.
Mind blown?
Yep.
What is the meaning of mind blown? What happened to your mind?
Tak
Explode,
macam
explode already.
I learned this during diploma and rupanya
Oh, you are direct entry.
Yeah, direct intake.
So
And
just if you are direct entry from polytechnic, this is kacang lah.
yeah.
This is kacang, right? I know
Yeah.
that because during my diploma, when I did my diploma, I got a classmate from polytechnic. When we learn about applied thermodynamic, we always refer to our friends from polytechnic on this applied thermodynamic because they learn everything the same thing. Okay, but sometimes it should we have to adjust it, especially in terms of the terms used, the symbol used. Maybe you are using different terms, different symbols during your diploma.
True, doctor. True.
So meaning that you are going to target A+ now, Tiba, for this subject.
Boleh doctor, try.
This is revision for you. Okay, this is just revision for you. Okay.
Okay, doctor.
Alright. So kalau tak ada soalan, I'm going to proceed with our next part. And before we go for the next part, I want to review back what we have learned in our thermodynamic. Remember that we learned something on the mixing process in thermodynamic. Remember, we have a mixer. We have a chamber. This is our chamber. And we mix same fluid with different energy. Okay, so this is the mixing chamber. Right? Let's say this is a 0.1. This is 0.2. And this is 0.3 or state 3. From state 1, we have, let's say, we have a hot fluid with a mass flow rate of M1. And at 0.2, we have the mass flow rate of M.2. Okay, and of course, at state 3, we have the M.3. And when we apply the mass conservation, this M.3 should be equal to M.1 plus M.2. Assuming that our mixing chamber is insulated. If insulated meaning what? Meaning there is no heat transfer between the mixing chamber and the surrounding. Okay, there's no heat transfer between the thermodynamic system in the mixing chamber and to the surrounding, or vice versa. And of course, this mixing chamber, just a mixing chamber, there's no work needed, there's no work produced. Right? So as far as the energy balance is concerned, we could write that energy balance through the steady flow energy equation. And what is that? The energy in equal to the energy out. So if we try to write down this energy balance, then we have this type of equation. M.1 H1 plus m dot 2 H2 equal to m dot 3 H3. So these are the energy equation or the energy balance equation incorporate with this mixing chamber. Okay? Right. So this is just a recap back what we have learned in thermodynamics. This is the mixing chamber. Another device that we have learned in thermodynamics is this device. I don't know what you call this device. I want you to call it. Can you recall back what we have learned? Flow in, flow out, flow in, flow out. This liquid in, the horizontal liquid in, is going into a passage or into a coil or into a pipe entering to this chamber. While this red flow is going into the chamber without mixing with the blue flow, but what is going to do is to transfer the heat to this blue line. Okay, so the red flow, this is the red flow flowing outside the blue line. Okay, this is the flow of the fluid, of the red fluid. Let's say this is state 1 and this is state 2. Okay, and then this is state 3, this is state 4. So this is m dot 1, this is m dot 2. This is m dot 3, this is m dot 4. According to the mass conservation, as for the rate flow, the m dot 4 is equal to m dot 3. And the m dot 1 is equal to m dot 2. Because it's separate passage. It does not directly mix. There is a boundary that separates these two fluids, the red fluid and also the blue fluid. Okay? And when we apply the SFEE to this device, the flow device, okay guys, can you give me the name of this flow device?
Heat exchanger.
Yes, heat exchanger. Okay, heat exchanger. So let us look the analysis of energy balance or the SFEE. Again, we are going to insulate, meaning that there is no interaction of heat transfer between the surrounding and the thermodynamic system inside this heat exchanger. So, energy in m dot 1 H1 plus energy in m dot 3 H3 equal to the energy out m dot 2 H2 plus m dot 4 H4. So this is the energy balance equation. Okay, the energy balance equation. Right. as far as the steam cycle is concerned, this device is being used in our steam cycle in order to increase the thermal efficiency. And the first device, which is the mixing chamber, this is called as the open feed water heater. Okay, this is being called as open feed water heater, which is the general name is mixing chamber. While the heat exchanger, this is referred as the closed type of feed water heater. I repeat again, these are the devices or the flow device that will be incorporated in our Rankine cycle in order to increase the thermal efficiency. Okay, remember, we have learned about Rankine superheated vapor, Rankine multi-stage expansion with reheat. Both cycle is for increasing the W net. Okay, to increase the W net. But when we incorporate this device into our Rankine cycle later, this device is being used, whether it's being used alone or multi-unit or mix of these two units in our Rankine cycle. The purpose of this usage of this feed water heater is purposely to increase the thermal efficiency. So you need to understand which method is being used to increase the work net, the work output, and which cycle, which component incorporated in order to increase the thermal efficiency. You must understand that. You don't mix it up. Okay? Don't mix it up. Okay? So this is the principle. This is the principle. So after saying that, now what are we going to look what is called as the regenerative cycle? Okay? Regenerative cycle. So this is the regenerative cycle. Not this one. I'm not going to look at this cycle, but I'm interested on this cycle. This is what been said just now. What I have explained for the mixing chamber, which is called as the open feed water heater, I'm referring to this device. Okay? So in a regenerative cycle, using open feed water heater, so this is our mixing chamber, what happened is we have expansion process in the turbine, while the steam is being expanded in this turbine at one intermediate pressure, which is P6, some portion, some mass flow rate from this turbine is being bled off and flow into the feed water heater. Let's say the bled steam from this turbine is YKG, meaning that from point 6 to the right, the balance of the mass of steam, which is 1 minus Y, is going to be expanded at the rest of the section of the turbine. So as though that we could put in section of this turbine, whereby this section having 1 kg of steam flowing, okay, and the next section to the right, the amount left being further expand is 1 minus y. Why 1 minus y? Because some of the flow is being bled off at 0.6, which is y kg. So the balance is 1 minus y. This 1 minus y is going to the condenser, and then it's going to be pumped up to the pressure of 6. So this is the first pumping process from the condenser pressure to the feed water heater pressure, which is equal to the pressure of P6. And then once combined, this is y kg. The flowing here is 1 minus y, 1 minus y, 1 minus y. When y plus 1 minus y, what is coming out from the feed water heater is 1 again, which now the state is 7. Okay, the state is 7. Then going to the second stage pumping process, where it will pump from the intermediate pressure up to the boiler pressure. Then going into the boiler, heat up until saturated vapor, and then going into the superheater, coming out as superheated vapor at state 1. And everything repeat again and again and again. And when we sketch on the Tts diagram, then this is what it would look like. 1 to 6, first expansion process for 1 kg. 6 to 2 is the second expansion process, which involves 1 minus y. This is 1 minus y. And then the same portion of 1 minus y is going into the condenser, 2 to 3. And then we have first pumping process 3 to 4, right? And then after that, from 4 to 7, we have increase of temperature. You see right here? This is increase in temperature. And this increase of temperature is because of the usage or the integration of the feed water heater. So this increment of energy in terms of the enthalpy or the temperature is because of the usage of this feed water heater. And then we go to the second pumping process. Then we go to the boiler superheater again and again. So our concern is mainly the portion of the flow involved for each section. It's no more 1 kg. Upper part 1 kg, intermediate part is the y kg, and the lowest part is 1 minus y. Okay? And if we look carefully, what happened actually, we have increased the temperature of the beginning of Q in. Now the Q in is not from 4, but the Q in now is started from 8. So meaning what? We have reduced the Q in energy. We have reduced it. But the same amount of power, the same amount of work will be produced. So if we have the same amount of W net, but we reduce the Q in, what happened to the thermal efficiency? Guys, what happened to the thermal efficiency? We make the Q in less with the same amount of W net. What happened to the thermal efficiency?
Increase.
Yes, it will increase. So the incorporation of this feed water heater is to increase the thermal efficiency. After saying that, I think I'll stop now. I will give you our attendance.
Saya ada soalan, sir.
Sekejap ya. Let me copy
Okay.
first this our link for the attendance first, so that
Okay, sir, no problem.
so the attendance is in our chat, yeah. To everyone, Control V. So guys, that is your link for your attendance for today. Okay. So what question is that?
Sir, why pumping process results in increase in temperature, sir?
Well, actually,
3 to 4.
we just call it as increase in temperature, but actually, what is increased is the internal energy.
Oh,
Because
okay.
you know that the internal energy is a function of temperature,
Yeah.
kan? Jadi
Yes.
maknanya kalau kita increasekan the temperature, meaning that we have increased the internal energy. And that is what we want sebenarnya. We want to increase the energy. But
Okay,
the effect of increasing the U value, the temperature will increase. Kalau ikutkan sini, memanglah temperature akan increase. Tapi sebenarnya kalau kita lihat, the enthalpy will increase. Because our interest is more towards enthalpy. Why enthalpy? Because this is open system. Kalau open system, kita ada dua jenis tenaga. One is internal energy plus the flow energy. Kan? Enthalpy is equal to U plus PV. This is PV is the flow energy, the energy needed to create the flow apart from the internal energy itself. And this, the internal energy is the molecular state of the substance ataupun in our case is the water itself.
Okay, sir.
Okay?
Okay, sir. Thank you, sir.
Welcome. Any other question, guys? Okay, kita dah discuss only for open feed water heater ya. Nanti kita akan discuss lagi lah. This is for your information kan, for all. This is the famous question to exam tau. Kalau exam ni keluar regen. Kalau exam ni mesti keluar regen. Yeah? I tried to change lah ya. I think last session also I think is regen. Tapi dah lama tak keluar adalah yang reheat. Tapi saya tak buat, saya tak tahu lagi siapa buat soalan untuk exam ataupun untuk test. And one more announcement kan guys. Our class on Wednesday is at 12, right? Betul tak? Our class at Wednesday.
Betul.
Okay. So our class in